Here. All right. Got your test back. Good work. If you're not happy with it, you'll have a chance to redeem yourself on the final exam. So, or if you're happy with it, that's awesome. You'll get to see it again on the final exam. So if you have questions about test 2, maybe we'll just hold off until Monday when we do our review class. And then you'll have a chance to review your test and just kind of bring some questions for the review class on Monday. And then we said, because we're going to squeeze functions in today, which is our last section, which is also the only new thing that you haven't been tested on the final exam, right? And so that's kind of fun to know that after today, you'll have seen it all. You got an overview. You can do this. You can get a handle on it. And so we kind of I could stretch it out over 2 days, but decided not to, because then we can have no class on the Friday. All right. Oh, I should say, if you want, I do have blank copies of test 1. I have a lot of version 1 and one version 2. So you want to grab a blank one, maybe of a different version. That might be fun. Relive the magic. Okay. And everyone has a functions handout, I think. Yeah. Good to go. All right. So functions, you've probably seen functions before. Functions are things like f of x is, I don't know, mx plus b is a function, a line is a function, right? That's function notation, which we've kind of avoided so far because we haven't technically talked about functions. And so we've talked about functions, but not called them that. Today, we're just going to introduce some rules around functions and properties of functions. So, you know, nothing this easy, but it is really fun to deal with functions. Just the properties of functions and the inverses of functions and the composition of functions. And then we're done. All right. So what is a function? A function, let's see here. Can I make this a little bit bigger? I know you have it, but a function from a set A into a set B. So we say into a set B is a relation. That sounds familiar. We just had relations on the test, right? So now this is an extension of relations, really, from A into B, where each element of A is related to exactly one element of the set B. Kind of a special case of relations. So the set A is called the domain of the function. And you've probably heard about the domain of the function in terms of a graph like this. All the values of x make up the domain, right? If you're thinking about a graph, thinking back to graphs, then f of x, which is also y, is the output. I'm not calling it the range for a reason, okay? Because technically, the set B is called the codomain. I'm not going to write either on the graph here because we're kind of working up to it. But so the things we map from are the domain, and the things we map to are the codomain, okay? As opposed to the range, right? We're used to saying the domain and the range. Spoiler alert, fine. The range is a subset of the codomain that is actually mapped to, right? And so, but we'll deal with this first. So a couple of key things about functions is that each element in the set A, which is in the domain, must be related to an element or some element of B, the codomain. Okay? And so what that means, or what that looks like rather, and I didn't give us very much room. I really wanted it to be 3 pages, but I spilled over to 4 pages. So that's what I was going for. Shortest. But we can have something like this. And remember, relations, we use something like a little bean here. And we can have, let's say, 4 elements in A. Okay. So these make up, oops, that was a weird, all those values make up the domain. That is a beautiful curly bracket. Wow. You don't see that every day from me. Nice. Mapping to B. Let's say we have 1, 2, 3, 4, 5. Let's get crazy. 6, squeeze one in. Each element in A has to be related to some element in B. Okay. So can look something like, we can do kind of the cleanest drawing of this because why not? Then this whole stretch is called the codomain. But these values, oh, that's bad. These values that are being mapped to, we will call it the range. We don't introduce the range until later, but just so you can see it kind of first glance. Okay. So you can have elements in your codomain that aren't being mapped to, that's okay. But the rule is that every element in A has to have some sort of mapping. Okay. So all elements in A must be, and I'm going to say used in quotes because I think that's kind of more useful than the definition, right? Just thinking about, okay, every element in A has to be used in this function. What about this next? So is related to exactly one element of the set B. Technically, what that means is if AB is in the set, is in F, so in the function F, and AC, so A maps to B, and A maps to C is what this says under F. Let's do this. Same notation as for relations, right? Under F. So if A goes to B and A goes to C, then B has to be equal to C. So you can't have A going to the first one and the second one. It can only go to one value in the codomain. So the second point is an element in A can only map to one element in B. So if we start off nice and slow here, if we have the set A is -2, -1, 0, 1, 2, and B is 0, 1, 2, 3, 4, then we can define S as this relation, right? S, we could determine if S is a function from A into B. Okay. And so maybe this should probably say, is S a function from A into B? Let's do that instead. That's more helpful. It is. It says so. But let's show why. So what we're going to do is you're going to have, because it maps from A into B, and so A is going to be your domain, and then B is the codomain. So I'm just going to list these values. I guess I should have listed them first before putting the circles around. Let's do that. Negative. Because we're mapping from A into B. If we're mapping from B into A, then B would be the domain. And B is 0, 1, 2, 3, 4. We can map this relation, right? S, we can draw it. -2 goes to 4. Let's see here. -1 goes to 1. 0 goes to 0. 1 goes to 1. Alarming, right? Initially, but that's okay. They're allowed to map to the same output, right? They just can't have, you just can't have something like this. Oops, this should be red. You can't have something like this where one splits and has two opposite or two different outputs. That's not allowed. But in this case, and then the last one, 2 goes to 4. All right, we can talk about, is this a function? It is a function. S is a function since, what's my checklist? Each element in A is used, and every element in A only maps to one element in B.
So if B into A, it's false.
That's right. B into A in this case would, so the inverse of S would not be a function, right? Kind of the reverse of S. But this way is a function. So all elements in A are used, and each element in A only maps to one element, only maps to one element in B. I didn't introduce the term mapping, but I think it's pretty intuitive. You know, A maps to B, that kind of thing. We're going to talk about the image of an element, but that's the same as mapping it. And so I'll introduce this notation. We're not really going to use this notation. We'll use function notation instead. And so we have this kind of, if f is a function from A into B, we could write it this way, but we rarely do. And if we do like this, right, to introduce a question, then you'll probably just be able to gloss over it and get to the question anyways. It's just establishing that A is the domain and B is the codomain. So the image of an element is all the outputs. So if f is a function from the set A into the set B, if A is an element in A, then f of A, which is the first time we're officially seeing this function notation, f of A, is used to denote the element of B that A went to or maps to or is an image of. So f of A is called an image of A or the image of A under F, if you want to be really picky about it. Okay. Usually we just say f of A and it's implied that F is a function and A maps through F onto B. Okay. And so really all we need to take away from this is this relationship, right? An element of A in the domain is going to map to B. An element A in A maps to B under F. A is the input, B is the output. Let's say that f of A equals B. A is the input and B is the output. If we're given A and B, two sets, these are the same sets that we've seen before, and S is this function again, then if we have to find the image of -1 under S, really what we're asked to find is S of -1. So if I give it an input of -1, I get an output of 1. Can do that. From earlier, 2 and 3, like we said, are not being mapped onto. That's okay, right? It just means they're not in the range. Yeah? And so here, in general, S of capital A is the set, right? Whereas a lowercase a is an element in capital A. Okay? And so capital A is the set, whereas versus S of A, whereas A is an element in A. Okay. S of A, capital A, the set A, is the set of 0, 1, 4. Those are all the possible outputs. Oops. Notice 2 and 3 are not images of any element of A. We might also notice, you have to think about, is there a relationship between the input and the output? If I give it -2, I get 4. If I give it -1, I get 1. If I give it 0, I get 0. If I give it 1, I get 1. If I give it 2, I get 4. Could probably summarize this as A squared, right? I give it A, it returns A squared. We might also notice that S of A is A squared. It takes an input of A and it squares it. I feel like introducing the range versus the codomain this way is pretty straightforward, right? The difference between the two. So the range is just the values that are being mapped to. Technically, the definition of the range is here. If f is a function that has domain x and codomain y, then the range of f is denoted by f of x, right, with all the inputs of x. And f of x, which is the set of x's, is f of a such that a is in the set of x, right? So the outputs such that a is in the domain, okay? Which is going to be the element b in the set y such that there exists an a in x such that f of a is equal to b. Yikes. They're saying the same thing, okay? But I'll say, or see image above, or I shouldn't say image, I guess that was incepted, I think, from the terminology. See drawing above. As long as you understand the difference between the range and the codomain, I'm happy. And so don't worry about that definition, but it's nice to kind of be able to pick that apart, but let's not waste any energy on it. Got bigger fish to fry. But we do note that the range of a function is a subset of its codomain. Yeah.
Just what does it say about green text, for example, too?
Here.
Yeah.
Notice 2 and 3 are not images of any element of A. Images. I'll clean it up. Wait, try to. I'll make a mess first. There. So it does have this kind of complicated definition technically, but we just need to understand it. Not yet. I'm in a marathon work week. So today or tomorrow I'll post it. But you'll have until the final exam to do it. I'll make it due the night before the final exam because obviously you'll need to probably do it before the final, but I don't really care when it happens. So you'll have lots of time to do it. So yeah, it went pretty low on my priority list, but I finished marking, so that's pretty good, right? Thank you. Oh, flatter. If A and B are both the set 1, 2, 3, and we have f is the, well, potentially a function, f is the relation, right? A function is a special case of a relation. So f, let's start off as a relation. 1 goes to 2 and 2 goes to 3. We want to know, is f is a function? Yikes. I even read through these. That's the problem when I know what I'm supposed to be saying, I think. Is f a function from A into B? 2 rules, right? Every element in A has to be used, and it can map to only one element in B. Okay. So let's draw it out. I find that the easiest thing to do is just to draw it out. And I didn't give you very much room, did I? There's probably cooler ways. Could do it like 1, 2, 3 or something. 1, 2, 3. But I'm stuck on these beams. I call these beams. I don't know why. So F is going to map 1 to 2 and then 2 to 3. kind of a problem. This is not a function. Since I'll say generically, not all elements of A are used, right? The 3 isn't being used. Not a function since not all elements of A are used. 3 is not used. So it's a relation, but not a function. Where can I put that here? Can I scoot this all over? Besides my edit. I edited it. There. Therefore, F is a relation, but not a function. There'll always be relations, right? Not necessarily functions. Same scenario again, 1, 2, 3. Mapping to 1, 2, 3, and we've got G. I think the easiest way to figure out if it's a function is just to look at it, right? So again, 1, 2, 3. Here we've got more room. A, 1, 2, 3. B. And I've got this relation G. Wow, that's sloppy. Okay, 1 goes to 2, 2 goes to 3. Oh, 2 goes to 1, but I stopped there. 2 can only map to one thing, right? Otherwise, it's not a function. We could keep going and say 3 goes to 2 and finish the list, right? Just for completeness sake, but we would stop here. Not a function, since 2, 3 and 2, 1 means 2 maps to 2 values, which is not allowed.
Has to use only once, and every element has to use once.
Yeah, every element of A. We're allowed to leave kind of empty slots in B, but every element in A has to be used and can only have one line from it, basically. Nice. Pardon? Oh, here? Nice. It's true. Yeah. Isn't it pretty cool? Can read these things. I think that's pretty cool. For all A and B in the set A, where A is not equal to B, that implies that f of A is not equal to f of B. I introduced the definition before we talked about it, but a function is injective, okay, if, so here it's injective if for every A, so for all A and B in the set A, so for every A, B in the domain, if A and B are different from each other, we assume, then the outputs have to be different from each other as well. Okay, that's a special case, and we usually just call it a one-to-one function. Oops, I shouldn't So we can call it an injective function, but I think calling it a one-to-one function is a little bit nicer and more understandable. And so what does that mean? Here. Every input, right? If these are unique inputs, or yeah, inputs, then the outputs have to be unique, which means that we cannot have this type of, where is it? Well, I think I erased it. We can't have, oh no, we can't have this type of situation where two things map to one, right? Has to be one-to-one. Right? One goes to one and one goes to one, the other way, one-to-one. So this means, so one-to-one, each output is mapped to at most once. You're still allowed to leave some out, right? And not map to them at all, but you can't map to it more than once. So each output is mapped to at most once. And just notice that we're talking about the output now. Has to be a function. It's a special case of the function. So here, a function. Oh, not what I was going for, but kind of cool looking, I guess. Must be a function. Right. Now, a one-to-one function is a special case of a function. And so what does a one-to-one function look like? If you have A and you've got 1, 2, 3, let's keep it nice and 1, 2, 3, 4, just to illustrate that. Could have just the, could have some missing. And I'm going to copy and paste this to show you the two. So one-to-one, they don't have to go straight across, but it's cleaner looking, right? And so this is one-to-one versus maybe something like this. Not one-to-one.
Exactly.
Yeah, just one-to-one. And so what that means is if the output of A is the same as the output from B, then A must be equal to B. And so usually what we do is we use this property to show that a function is one-to-one. And I don't do it until the end, but we will use this property to show F is one-to-one. So we'll be able to show or prove if F is one-to-one or not. Yeah. Less important because we can always force it. So I was talking to Steve about this because I was like, well, I guess I should save the story because I need to talk about bijective, but we're about to introduce surjective functions. So a bijective function is both injective and surjective. And so I'm like, why does it have to be surjective, or why do we have to say that? We can't really prove it. But then he was like, well, we can always force a surjective function. So what is a surjective function? It is surjective if its range, f of a, is equal to its codomain, meaning there are no kind of free agents roaming around in there, right? And so if, whoops, now I don't want that. So if all the mappings use up everything in B, then it's a surjective function or an onto function. Everything maps onto something in the codomain. So we could look at the definition here. So for all B in the set B, so for every element in the codomain, there exists an A in the domain such that if I give the function the input A, it'll return some function, some element B for all B in the set B, which really just translates to every element in the codomain must be mapped to. Do I have? Where can I sneak this in? Already made it super small. There. No space. What do you need to do if you had this situation? So now, if we need to force it to be onto, all right, I could exclude one of these points, right? And then each one of these would be mapped onto exactly once. So here we could, or let's just add an element in A. We don't really do that, but for this, none unused is what that's saying. So there are nothing like this. Really zoomed in. So it doesn't have to be one-to-one to be onto, but to be bijective is if it's both injective and surjective. So usually what we call these are one-to-one onto functions. So they're a special case of functions.
So that was a bad example.
How so?
It is one-to-one.
It is one-to-one and onto in that case.
So that's bijective.
Let's see if I can think of, it is bijective. What would it look like if it was not one-to-one, but onto? Let's do that. This one can go here, this one can go here, and this one can go here. I cannot. What would need to be true? Or how about less dots on B? Let's do this. You can have that. Why? I can have A goes to this little guy, or first one, this one, and then maybe that one goes there. Not one-to-one. It is a function, right? So it is a function because every element in A is being used and every element in A goes to a unique or goes to only one element in B, I should say, not a unique element, but a one element in B. Okay, so this is the trickiest one to get a handle on. This is a function. I'll highlight that here. This is a function. Huh?
So that is surjective.
It is surjective, but it's not injective. So it is onto, but it's not one-to-one. Function, which is onto, but not one-to-one. You guys are so good using the proper terminology. Just use one-to-one and onto. So like, yeah, this one is surjective, but it's not injective. And then, what was I doing here? This one is one-to-one. So this is a function. It's one-to-one, but not onto. On the final exam, I'm going to use the terminology one-to-one and onto. If you want me to, I can put in brackets surjective and injective. But I think one-to-one and onto are kind of more clear. So both of these are functions, one or the other. And this case is both, right? One-to-one, and every element in B is being mapped to. So it's both. This one is both. Or bijective, I guess. I really, really needed more space. But I was pretty hung up on, how about I move this to the bottom? And then it'll be in there, right, just for some examples. But I do find that this one is the tricky one, trying to convince yourself that this is a function still, and it is, right? Let's do this example. If A is 1, 2, 3, and B is A, B, C, D, and we define A into B by f of 1 is B, f of 2 is C, f of 3 is A, is F a bijection? Well, let's see. We can still use our little beans here. A, B, C, D. Okay. If I give it an input of 1, I get an output of B. 1 goes to B. If I give it an input of 2, I get an output of C. If I give it an input of 3, I get an output of A. Is it a bijection? No. What about 1-to-1? Can be 1-to-1. You're allowed to have a leftover in 1-to-1. You just can't map to, so two different things can't map to the same thing. That's the only condition of 1-to-1. It is 1-to-1, but D is not mapped to. So it is not onto. Therefore, not a bijection. Sneaky. If a function is 1-to-1 and onto, what do you know about the sizes of those two sets? They'd have to be the same, right? The domain and the range / codomain, because in order to be onto, the range has to be the codomain, right? And so then we can talk about the cardinality, which we have seen before, right? Two sets have the same cardinality if there exists a bijection between them, right? They're the same size. If a set has the same cardinality as the set 1, 2, 3 to n, then we say its cardinality is n. What's interesting is this is actually technically how we count things, right? If I have to count how many handouts I have, right, in the set of handouts, right, then what would I do? I would be mapping from our number system, right? 1 goes to the first one, 2 goes to the second one, 3 goes to the third one, and so on and so forth. And so technically that's how we count things, is by mapping from our number system to the items in the codomain. So that's kind of cool. Obviously not something that we need to go deeper into, but I think it's kind of a fun thing to think about. Two functions are equal if and only if, and you've got this already, right? Two functions are equal. If I asked you just to think about what does it mean for two functions to be equal, you would probably say something like, oh, if I give it the same input, I should get the same output, then they're equal, right? And so that is exactly what it is. So if f of x is equal to g of x for every x in the set A. So even though functions look different from each other, right, because we can rearrange things and do cool things, they can still be equal. So if you have some functions h and k, where h is -1, 0, 1, 2, and it goes to a set 0, 1, 2, we can look at the absolute value of x. Is h of x. The absolute value of -1 is 1. The absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. All right, checks out. And if k does the same thing, but it maps from -x⁻³ over 3 plus x squared plus x over 3, right? These things don't look the same at all. But if you go through and you plug in -1, I guess technically from this set here, but they're the same, right? You should get 1. And if you plug in 0, you should get 0. And if you plug in 1, you should get 1. And if you plug in 2, you should get 2. So I didn't try it, but I trust that they know what they're saying. Okay. So for every same input, you get the same output, and then they're the same. Same. I forgot I could sit down. That's nice. Oh, long day. All right. You guys done function compositions? We've seen compositions of relations, and so this is really just an extension of that with some caveats, I guess. So if we have a function f that maps from A to B, and then we are going to daisy chain, right? From we give it a function g, which takes B to C, right? Then the composition of f followed by g, we write as this g composed with f is how it's read. But I just read it as g, technically it says g composed with f. Or if you're lazy, g of f. I just read the circle as an of. That's lazy, but technically true, because so g composed with f takes A to B and then B to C, and goes, so it takes from A and returns C or something in C. And so how we define it is we have g composed with f of x, so I give it some input, is the same as g of f of x. Okay. And so usually this is how I break down my function compositions. I find that it's a little bit easier to read than the g composed with f and then of x. And so I like this second version, but it's up to you. Okay. And I do expect you to be able to read both versions. Okay. So usually we write the composition of functions from right to left. Yeah. And so here, what that means is you're going to start at f and put it into g. Right? Technically, you're going to start with putting in x into f and then putting f of x into g. Right? And then that's how you're going to go from A to B and then B to C and end up at C. Okay. Which is different from relations. So when we had a composition of relations, RS, that meant that we applied R first, then S. And so it's backwards, I guess. Okay. I might need a little bit more room here. I'll kind of scoot this down here. There. So if I have f taking from 1, 2, 3 and mapping to A, B, and we're going to just define it as f of 1 is A, f of 2 is A, and f of 3 is B. And then we've got this g, where g of A is 5 and g of B is 7. We're going to list all the values of g composed with f. And so first thing I want to do is g composed with f. Oops. I'll make a column, because then we're going to do f composed with g over here. So g composed with f of 1, which is the first element of f, is the same as g of f of 1. what we need to do is you need to start here. Well, I mean, technically start by putting in and evaluating f of 1. Okay. And so here, evaluate f of 1 and use it as the input into G. So I do it this. F of 1, we were told, is A. So really what I want to evaluate is G of A. And G of A, we were told, was 5. What if we want to find G composed with F of 2? That's the same thing as G of F of 2. F of 2 is A again. And G of A is 5 again. So really, we're going from an input of F and we're ending at an output from G, right? Kind of hopping. And for our last input of F, G composed with F of 3, that's the same as G of F of 3, which is G of F of 3 is B, and G of B is 7. What about F of G of 1, or sorry, of A rather? Has to be an input of the kind of outermost one, or the rightmost one.
Oh.
So
5.
this, we can rewrite it as F of G of A. So F of 5, but F only takes values from 1, 2, and 3. And so this does not exist. So here, that means that G composed with F is not the same as F composed with G. We're no strangers to that type of situation, right? We know that the matrix of A times B is not the same as B times A, right? We've seen that before. And so it's kind of the same situation, right? And so notice G composed with F of X is not the same as F composed with G of X, or some version of that. Good. What if we had a more grown-up function? F takes an input from the set of real numbers. The set of real numbers is what? Set of real numbers is from -infinity to infinity. And it maps it to -infinity to infinity. All right, so here. So we're mapping from the set of real numbers to the set of real numbers. And we're going to let f of x be x to the 3. That's cute. And we're going to let g do the same thing, map from r to r. And g of x is going to be 3x plus 1. Let's find g composed with f of x. Taking it nice and slow. And then we're going to also find f composed with g of x. First thing I always do is rewrite G composed with f of x as just G of f of x, because I think it's nicer. But you can use either. You don't have to use both, or you don't have to do both at all. Just one of these notations is fine. G of f of x, first thing I want to do is I want to figure out the output of f of x. The output of f of x is x to the 3. Right? So I have G still on the outside, but I want to evaluate G at x to the 3. So wherever I see an x in G, I'm going to input x to the power of 3. So this looks like 3 times x to the power of 3 plus 1. And that's G of f of x. Is that a question or a... You're allowed to have a... Take a moment.
I thought it was going to be 3x plus 1. That will be 1 power of 3 all together bracket outside.
That's f of G of x. Jumping the gun here. F of G of x is f on the outside, G on the inside. So then I replace G of x with 3x plus 1. Keep f on the outside, 3x plus 1. Now, f gets an input of 3x plus 1. So if I plug that into x to the 3, wherever I see an x, I replace it with 3x plus 1. So I get 3x plus 1 to the power of 3. These are not the same thing, right? This simplifies to just 3x to the 3 plus 1 if we ditch the brackets, but this would, and I'm not going to do it, 3x plus 1 times 3x plus 1 times 3x plus 1. Yuck. Although I enjoy foiling or feeding the chickens or whatever you want to call it, but these two things are not the same, right? Uh, 3x to the 3 plus 1 is not the same as 3x plus 1 times, let's just do to the power of 3. What this says is therefore not commutative. I'm not going to use that term, but it just means that you can't swap the order, right? The order matters. But I wanted to put it on there because I can't remember what the assignment questions look like right now, but they might say it, and so that's why I wanted to introduce it. I will introduce the term associative. And so function composition is associative. And so kind of skipping to the meat and potatoes here, what that means is if I have a function h composed with g composed with f, if I do g composed with f first and then compose it into h, that's going to be the same as h composed with g composed with f. And so here, the brackets, the order doesn't matter. Right? Brackets don't matter. It's the same thing as multiplication, right? We're used to seeing things like a times B times C is the same as A times B times C. Right? That's associative. So it's the same. How can I do this? And why did I make it so small? So using the same functions, but I've tacked on a function h, and I just let h be 2 times x. Little cutie. Then we're going to find h composed with g composed with f, but the brackets tell me that I have to find g composed with f first and then put it into h. Okay. We already have g composed with f from up here. It's 3x to the 3 plus 1. So here, so we can sneak those in here. H of g of f of x is wherever I see an x in h, I'm going to replace it with 3x to the 3 plus 1. So I get 2 times 3x to the 3 plus 1. What if I first find h composed with g? H composed with g means I'm going to put g, 3x plus 1, into 2x. And so this is going to be h of 3x plus 1, which is 2 times 3x plus 1. What did I do here? I did something weird. I did it here, but it looks like it's supposed to work. Oh, I see the problem. There's no problem. This composed with f means I'm going to put f into this. And so wherever I see an x, I'm going to replace it with x to the power of 3. So now let's do this. H of g of notation. I'll just do this. Composed with f of x, which is x to the 3. So wherever I see is at x to the 3, you do get 2 times 3 times x to the 3 plus 1. They are the same, just tricky. I'm not going to make you do function compositions for 3, but I will make you do function compositions for 2 functions, obviously. But that's like this, not like this. Yeah. 3 is too many. You can do it, but that's not a test question. That's really all we have left, so, or a final exam question, so I'm not going to do that to you. Right. As long as you can do, and there's even a special case of function composition that we're going to focus on, which we're getting to. Okay. A composition of injections is an injection. So if you already have 2 injections and you compose them, the result is still an injection. Fair. Same thing with the surjection, but we're not going to really bother with that. What we're going for is the inverse of the function. So we're building up to that. So if we think about the real numbers, 0 and 1, if I add 0 to some value, it stays the same, and it doesn't matter which order I add 0 in, it stays the same. I can multiply by 1, right, and still get the same value back. Okay. And so what we say is 0 and 1 are identity elements for the operations of addition and multiplication. We saw the identity matrix in matrix algebra, right, where we can multiply A times the identity matrix, and we can get A, and we can add the 0 matrix to A, and it would just say A, nothing happens. And so we can do the same thing for functions. But first we need to identify the identity function. For any set A, the identity function on A is a function from A onto A, denoted by I, so a lowercase kind of script I, or technically I subscript A, but let's just use I, which the function I takes an input A and returns A for every element of A in the set A. Okay. So it's a special function that takes the input and returns the input, right? And the output becomes the input. So output is the same as the input, right? We need that for the inverse function. We have seen the inverse of a matrix, right? And so now we're going to see the inverse of a function. And so if there's a function g, where g is composed with f is the same as f is composed with g, and that equals the identity function I, then g is called the inverse of f. And it's denoted by f to the power of -1, or you read it as f inverse. We're going to call it the inverse because there's only one inverse. Okay. Can never have more than one inverse. What this is actually saying here is that f of f inverse of x should be the same as f inverse of f of x, and it should be x. We can do that. We just need to know how to find the inverse of a function. Okay. So let's get crack-lacking on that. And so the inverse of a function is the function that kind of undoes f. So whatever f does, the inverse of it undoes it. So it's not the reciprocal or anything weird like that. And so as an itty bitty example, we've got here. So if A is the set 1, 2, 3, and f of 1 is 2, and f of 2 is 3, and f of 3 is 1, then f inverse of 1 is going to take 1 and return 3. Because it's moving backwards. F inverse of 2, you look for an output of 2. Nice. And you get 1. And then F inverse, of 3 is 2. It's really the trip back from the range to the domain. Oh boy, lose my voice. Oh, good. I can be sick for the weekend. That's nice. I think I just talked too much this week. All right. So first thing we want to do is a function needs to be one-to-one in order to have an inverse. And so here of a one-to-one function, but here let's make a note. A function must be one-to-one. And technically onto as well, but like I kind of mentioned earlier, you can always just zip up your codomain and make the range the codomain and make it onto. And so we don't really test it, but I will show you how to show that it's one-to-one, right? And so a function must be one-to-one in order to have an inverse. If it's one-to-one, which I haven't really shown you how to check, but I will, then to find the inverse of the one-to-one function, first thing you're going to do is you're going to write y equals f of x. So just write out the function as in terms of y. And then you can solve the equation for x. So just rearrange everything, solve for x, and now your input is the y's, right? Just like we did here, right? Your input is the y and the output is the x's. And usually what we do is we interchange the x and y because we still want to talk about the inverse of x because x is traditionally just from the domain. And, but now I guess it's the range, but x is the input just generically. You can reverse these two steps if you want to, right? You can interchange x and y and then solve for y. That's doing the same thing. And so I've got these 3 examples for us to do, but let's do this last little bit of notes first. So if g is x to the power of 3, then g inverse is the function that undoes what g does. So if we follow those steps and find the inverse, right, we can write y equals x to the power of 3. Okay? That's the first step. We can solve for x. If I have to solve for x here, I get the third root of y is x. Third root, I don't need the plus minus because it's odd. So solve for x in terms of y, we did it. Interchange x and y. Therefore, f inverse of x is the third root of x. I'll do it this way. Find G inverse of x. Now, in order to prove that it is the inverse, we're going to show these two compositions. G inverse composed with G has to be the identity, and G composed with the inverse, its inverse, has to be the identity. And so let's start with G inverse composed with G is G inverse of G of x. Which is going to be, so I take G of x, which is x to the power of 3, and I'm going to plug that in here first. G inverse of x to the power of 3. Now, in G inverse, or what we think is the inverse that we found, right, I'm going to, wherever I see an x, I'm going to replace it with x to the 3. And so this becomes the third root of x to the 3. By exponent laws, this is x to the 3 times 1 over 3, which is x. Oh, G, thanks. There. Notice I only used F's here because I'm so used to doing F's. So that's good. That means that the inverse takes G and it just kind of leaves you with the input. And so that's a good first step, but we need to check it for both compositions because we know from function compositions that they're not the same. Right, and so G composed with G inverse is G of G inverse of x, which is G of x is x to the 3, but let's do G inverse, which is the third root of x. So in x to the 3, I'm going to replace any x I see with the third root of x to the power of 3. But again, exponent laws, x to the 1 over 3 times 3 is just x. Which is the identity, right? It is just x. Therefore, G inverse of x equal to the third root of x is indeed the inverse of G of x equal to x to the 3. Just because I'm going to snag these and bring them to the next page here. Oh. Need lines. Oops. Okay. So on the final exam, I'm going to give you a question just like this. Okay? You're going to have to show me that it's 1-to-1. Okay? You're going to have to find the inverse because it will be 1-to-1, I promise. And then you're going to use the inverse function property, which we just used, where if I compose the function with its inverse, I should get back to x. And if I compose the inverse with the function, I should get back to x. And so let's see here. What we haven't introduced yet to show f of x is 1-to-1. I'm going to scroll back up to the definition of 1-to-1 so we can kind of have a closer look at it. Where is it? Here. I did make a note. We're going to use this property to show f is 1-to-1. And so what we're going to have is we're going to use f of a and set it equal to f of b. If I'm able to unravel things and show that that means that a must be equal to b, then it's 1-to-1. F of a, you can just plug in a for x, but I like to do it at the center of the page. F of a is equal to f of b. And I take my specific function, f of x is 3x minus 2. So then I have 3x minus 2, or 3a minus 2, is equal to 3b minus 2. One. Set f of a equal to f of b. Start, I don't know, solving for a. Can solve for b too, but start solving for a. So if I'm solving for a, I would first add, I would first add 2 to both sides. 3a is 3b minus 2 plus 2. That's nice. So 3a is equal to 3b. Then if I'm solving for a, I would divide both sides by 3. So I get a is 3b over 3. And all of a sudden, a is equal to b. Step 3, if you find a equals b, f of x is 1-to-1. So that's kind of fun. You know you're looking for, because I'm going to ask you to show that it's 1-to-1, right? And so as long as you know to set f of a equal to f of b, then you know your end goal is to make a equal to b, right? Just solve for one of those two things and they'll just kind of unravel. Okay. So you can show that f of x is 1-to-1. Now that it's 1-to-1, then I can find the inverse, right? Since it is 1-to-1, we can find the inverse. I'm just going to jot down f of x was 3x minus 2. To find the inverse, first we're going to write y equals 3x minus 2. Right, y equals f of x. Just replace it with step 2. Sometimes I like to swap the variables here, but you're going to solve for x in terms of y. Or just solve for x. If I rearrange this thing, I get y plus 2 is equal to 3x. And then I use my equal sign revolving door here. 3x is equal to y plus 2. And so then 3x is equal to y plus 2. That's still true. And then solving for x, I get y plus 2 divided by 3. Interchange x and y. So then you get y is x plus 2 divided by 3 is equal to f inverse of x. Right, that's the function that undoes 3x minus 2. Okay. Use the inverse function property to show that the inverse you found is indeed the inverse. Okay. Show f inverse of x is equal to x plus 2 over 3 is indeed the inverse of f of x equal to 3x minus 2. I think it's minus 2. That means show that f of f inverse of x has to equal x, and f inverse of f of x has to equal x. I put x in the middle so I don't have to. But both of those compositions have to equal x. So you do them, usually I like to do them side by side to save some space. And so let's see here. F of f inverse of x. F inverse of x is x plus 2 over 3. And maybe I'll scoot this over. So I want to do f of x plus 2 over 3. So wherever I see an x in f of x, I'm replacing it with x plus 2 over 3 using brackets because you don't want to lose. This is one unit, right? And so you get 3 times x plus 2 over 3 minus 2. Things are looking up. 3 over 3 is going to cancel. So you're left with x plus 2 minus 2. Well, those two plus 2 minus 2. Eee. That's what we were going for. What does that mean? I'm halfway to showing that the inverse I found is the inverse. It also has to work because remember the opposite or kind of the switched composition is not necessarily the same, right? But if it is the inverse, then they both equal x. And so the next one I need to do is f inverse of f of x, which is f inverse of f of x, which is 3x minus 2. Wherever I see an x in f inverse, I'm going to replace it with 3x minus 2. Where is it? 3x minus 2 plus 2 divided by 3. I get 3x minus 2 plus 2 is going to cancel. So 3x divided by 3, which is also going to cancel. And I'm left with x. Boop, boop. Therefore, f inverse of x is indeed the inverse of f of x. I don't know about you guys, but I think these are very fun because you always know what you're going for, right? And so showing that it's onto, or one-to-one rather, right? You plug in, you set them equal to each other, you plug in A, you plug in B, and you know you're aiming for A equals B, right? And then you can find the inverse of the function, right? Just kind of rearranging things, undoing things, but then you're going to check that you got it right by using the function compositions. So that's nice. And I've got 2 more for you, but I think I'm reading the time right. Time flies when you're having fun. And so I'll post these in the notes and you'll have them, but you can try them on your own. These are a little bit more grown up, right? Here I've got f of x is x to the 5 minus 3 over 2x to the 5, right? A little bit sneaky. And then even something like this, a rational function, 2x plus 3 over x minus 1. Whew. But you can do it. Okay. If you have any questions, let me know. Otherwise, the end. You did it. No more new material. All right. Go enjoy your Friday. Or do some inverses. I don't know. Your choice. And I'll see you on Monday.